Hey guys, my name is IBM and today I'm solving a 9702 May June 2024. This is AS level structured questions, the May June series. So this is the question paper that I'm going to solve. It's May June 2024 970223. The answers may not be The answers to these questions may not be final, but I'm very certain they will be almost 99% accurate because I'll try my level best to use my experience. So without wasting time, I would go to the questions. Question number 1. The drag force Fd acting on a sphere falling through a liquid is given by Fd equals to 6 pi no r times V. Show that the SI base units of viscosity are given by kilogram per meter per second. So I always encourage my students to make the quantity whose units is required always the subject. So nu is the viscosity, and we want to find the units for the viscosity. So making nu the subject, so we have that nu is going to be equal to, I don't know how to write nu very well. It's going to be equal to the drag force Fd divided by 6 pi times, I've taken nu to the left hand side, so I'll say I'm leaving nu on one side, so it will be 6 pi times r, then times v. So I always encourage my students to list the units of each of the quantity. R is the radius, so the units for r are going to be meters. Then v is the speed, so the units for v are going to be meters per second. Then Fd is the drag force, so the units for Fd are going to be kilogram meters, that is for mass, times acceleration, which is kilogram meters per second squared. So now I substitute to find the units for nu. I always don't encourage my students to put equal signs on a quantity and its units. So the units for nu will be the drag force, which will be kilogram meters per second squared, divide by, I will ignore 6 pi in units, so I remain with r, which is meters, times meters per second. So I'm just going to simplify this further. So this will be kilogram meters per second power minus 2 divided by meters squared s power minus 1. So doing some simple mathematics, I know that m divided by m squared becomes m power negative 1. We subtract the powers. Then I have s power minus 2 divided by s power minus 1. I subtract the powers, so it will be s power minus 1. So the units will become kilogram m power minus 1 times s power minus 1 as required. The sphere has a radius of 3 centimeters. So that will be times 10 to the power of negative 2 to change it to meters. And is falling vertically downwards at a terminal velocity, which means the acceleration is 0, so the resultant force is 0. A terminal velocity of 2 meters per second through the liquid. The drag force acting on the sphere is 0.096 newtons. Calculate the viscosity of the liquid. So remember, we have already seen viscosity is equal to the drag force divided by 6 pi times r times v. So I'll just substitute. The drag force has been given as 0.096 divided by 6 pi times the radius, which is 3 times 10 to the power of minus 2, then times the speed, which is 2.0. So I'll press my calculator. 0.096 divided by 6 pi times 2 times 3 exponent minus 2. So this is giving me 0.085 or 0.0849. I'll just write two significant figures, 0.085. 0.085 kilograms per meter per second. Okay, the sphere is shown in the figure. Note that it is fully submerged, so the upthrust is of course constant because it is fully submerged. On the figure, draw and label arrows to represent the directions of the three forces acting on the sphere as it falls at terminal velocity, that is at constant velocity. Number one, the sphere has a mass, so it has a weight which acts vertically downward, so this is going to be the weight. Number two, whether the sphere is moving or not, there is a force due to the fluid, which is the upthrust. So there is an upthrust force which acts upwards, so this is upthrust. Number three, if the sphere is moving like it is said to be moving downwards, so there is a resistive force which is called the viscous drag. So I'll draw another arrow pointing upwards, and I'll call this the drag force. Or you can call the viscous force. The drag force, or call it the viscous force. Okay, the density of the liquid is 920 kilograms per meters cubed. Show that the upthrust acting on the sphere is 1.0 newtons. So, of course, according to Archimedes' principle, the upthrust is equal to the weight of the fluid displaced. But since the object is fully submerged, then the upthrust is going to be equal to the weight of the object itself, because a floating object or a submerged object displaces its own weight. So I'll simply say the upthrust is going to be the mass of the object times g, that is equal to the weight of the object, which is the same as the weight of the liquid or the fluid that it displaces. So it will be the weight, mass, which is density, times volume, that is the mass, then times g. But of course, we know that if it is a sphere, then the volume of a sphere is 4 divided by 3 pi r cubed. That is the volume of the sphere. So I'll just substitute. So the density is given as 920. The volume will be 4 divided by 3 pi. They gave us, I think, the radius. The radius was 3 centimeters, which is 3 times 10 to the power of minus 2. So this is 3 times 10 to the power of minus 2, and this is going to be raised to power 3. That is the volume, then times G, which is 9.81. So I'll just check with my calculator. 920 times 4 pi divided by 3. Then I'll first multiply by 9.81. Then times, I'll open the brackets, 3 exponent minus 2, but this should be raised to power of 3. So this is giving me a 1.02, 1.0207, and so on and so forth, which is approximately 1.0 to two significant figures, 1.0 newtons as required. Then calculate the mass of the sphere. Note that it is moving at terminal velocity, so I will say at terminal velocity, the resultant force is going to be 0. And the resultant force, if the resultant force is 0, it means the total force is acting upwards, which is the drag, plus the upthrust should be equal to the weight, which is downwards. So the forces are balancing. But remember, the weight is equal to mg, so I'll say mg, which is the weight, should be equal to the drag force. I think we have the drag force somewhere, and we have the upthrust is 1. The drag force is 0.096. So I'll say the drag force is 0.096 plus the upthrust, which is 1.0. So if I make m the subject, so m is going to be 0.096 plus 1.0 divided by g, which is 9.81. So I'll just press my calculator, 0.096 plus 1 divided by 9.81. So this is giving me 0.1112, 117, or approximately 0.11 kilograms. So I'll just write two significant figures, 0.11 kilograms. Question number 2, define a displacement. I think this is in one of the other papers. I think it was, I don't know whether it was paper 2-1, but of course I say displacement is the rate of change of velocity. You can define, oh, not this rate of change of velocity. Displacement is actually a distance in a specified direction, not rate of change of velocity. So distance from from the point in a specified direction, that is displacement. Distance from the point in a given direction or in a specified direction. So that is displacement. Alternatively, you can define displacement as the shortest distance, actually the shortest and straight distance from the point to another point, from one point to another point. So this is the shortest straight distance from the point which we are talking about to another point, from the point to another point. So that is displacement, the distance from the point in a specified direction, that is displacement, or the shortest straight distance from the point to another point or another position. An object is projected horizontally at a speed of 6 meters per second from a slope as shown in the figure. So maybe it takes that path, but then of course it is falling here. The slope is at an angle theta to the horizontal. Air resistance is negligible, which means our equations of motion can apply, because in the horizontal we know that acceleration in the horizontal is always zero since there is no force acting in the horizontal. If air resistance is negligible, then acceleration in the vertical is going to be negative g. No, it's going to be just g, because initial projection was horizontal, so it is just going to be g, which is 9.81 meters per second squared. The object lands on the slope at time 0.71 seconds later and stops without rolling or bouncing. Determine the horizontal distance traveled by the object. So we want to find the horizontal distance traveled by the object. If it starts from here and it falls here, so we want the horizontal distance. So this will be the horizontal distance. I will call it SX. And this is going to be the vertical distance. I'll call this one SY, which is the same as this distance here. So I'll use equations of motion. The common one is going to be S equals to UT plus a half AT squared. Of course, I'm considering horizontal motion. And when I put an X here, it means displacement in the horizontal. When I put an X here, initial velocity in the horizontal. When I put an X here, it is acceleration in the horizontal. So we have the initial velocity in the horizontal as 6. The acceleration in the horizontal, I've already said acceleration in the horizontal is 0 because there is no resultant force in the horizontal, since the only force acting on the body is the weight which acts in the vertical. So substituting the distance we are talking about here is going to be the initial velocity in the horizontal, which is 6.0, times the time, which is 0.71. Then of course this last part here, this part will be 0. So this is going to be the distance we are talking about. So 6 times 0.71. So this is giving me 4.26 meters, or approximately 4.3 meters. Then determine the vertical distance traveled by the object. So now I'm going to consider vertical motion. But I will still use the same equation, S equals to UT plus a half AT squared. So for vertical motion, I will say S in the vertical, initial velocity in the vertical, acceleration in the vertical. Remember, the acceleration in the vertical is going to be 9.81 because the body did not go above the point of projection, it just went below. So it means the acceleration is going to remain positive, not negative. So the vertical distance we are talking about here, which I've called SY, initial velocity in the vertical. Remember, it was initially moving horizontally, so initial velocity in the vertical is going to be 0. Its initial motion was in the horizontal. There was no initial velocity in the vertical, so this part here becomes 0. So I'll remain with the half times 9.81. Then where there is t was 0.71, but this is squared. So checking with my calculator, I will have a half, which is 0.5 times 9.81, then times 0.71, but this should be squared. And I'm getting 2.47 or approximately 2.5. So the distance is going to be 2.5 meters. Then use your answers in B and B Roman 1 and B Roman to calculate theta. So theta is this angle here. So I'll just sketch a triangle from the diagram. So we have the vertical distance. The vertical distance is of course downwards. The vertical distance was 2.5 meters. Then we have the horizontal distance, which we have seen as 4.3 meters. And then we have this is going to be, so we want to find the resultant of these two. So since they are at 90 degrees, I'll just use Pythagoras theorem. But of course, precisely the resultant of these two, if I prolong this direction downwards, and I prolong this one, so the resultant is supposed to be somewhere here. But of course, this angle, the angle I'm talking about here, theta is the same as this angle here. So the displacement is, remember, the shortest distance, the shortest straight distance. So we want this distance here. Or we want the angle between this and the resultant. So this is the opposite of the angle theta, and this is the adjacent of the angle theta. So if you recall from your math, so SOHCAHTOA, opposite adjacent, that is tan. So I'll simply say that tan of the angle theta is the opposite, which is 2.5 divided by the adjacent, which is 4.3. So what is theta? So I have 2.5 divided by 4.3. Then I get the tan inverse of the answer, which is 30.2. 30.2. So the answer here is going to be approximately 30.2 degrees. Alternatively, you could find the hypotenuse. You could find the hypotenuse from Pythagoras theorem. This would be square root of 2.5 squared plus 4.3 squared. That is the hypotenuse. So you can now use n, you can use sine, you can use cos if you have the hypotenuse, but the answer will be approximately the same. Then, okay, let's check. Of course, this will give us, let me first check this. 2.5 squared plus 4.3 squared under the square root is approximately 4.97 meters. So if I use cos, I will say cos of theta is equal to the adjacent, which is 4.3, over the hypotenuse, which is 4.97. And I think this gives us very close to 30, approximately 30 degrees. You can also use sine, which is opposite of a hypotenuse. You should be able to get almost the same thing. Then determine the magnitude of the displacement of the object from its original position. Of course, for the displacement, we have somehow got it from the previous part. We have the vertical distance and the horizontal distance. They are at 90 degrees, so the resultant is got from Pythagoras theorem. So magnitude of displacement is equal to the square root of 4.3 squared plus 2.5 squared. I think we have already got this as 4.97 meters. Or if you wanted to round off to a smaller number, we got 4.973. Or this is very close to 5.0, I think. 5.0 meters to two significant figures. So you can choose write 4.97, 5.0. The tolerance is determined by the examiners. So I'll just write here 5.0 meters. So the tolerance can be determined by the examiner, but 5.0, 4.97 is correct, I think. Then by considering energy, calculate the speed of the object just before it lands. By considering energy. So when it is falling, it has an initial kinetic energy, but as it is falling, it is losing gravitational potential energy. So as when I get its initial kinetic energy, also the loss in kinetic energy must be equal to, the gain in kinetic energy must be equal to the loss in gravitational potential energy. So I will say the loss, because when it is falling, it is gaining kinetic energy. So I will say gain in kinetic energy is equal to the loss in gravitational potential energy. So I will say gain in kinetic energy should be equal to the loss in gravitational potential energy. So what is the gain in kinetic energy? It has an initial speed, so it has an initial kinetic energy, and we expect it to have a final kinetic energy. So I'll say the final kinetic energy minus the initial kinetic energy should be equal to mg times the change in the vertical height h. So that is if there is no friction, there is no air resistance. So the final kinetic energy is going to be a half times m. Let the final velocity be v squared minus its initial kinetic energy was a half, the mass m, its initial speed, there was no speed in the horizontal, so its initial speed was, there was no speed in the vertical, the only velocity there was in the horizontal, so its initial speed is 6.0 squared. It doesn't look nice here. 6.0 squared should be equal to the mass, which is, we don't know, times g, which we know as 9.81. Then the vertical height, I think the vertical height is 2.5. Displacement in the vertical, because when you're finding the loss in gravitational potential energy, you consider distance in the vertical. So this is 2.5. We got 2.5 meters. So m cancels because it's a common factor. I'm remaining with the v squared, so I'm just collecting like terms here. So v is going to be the square root of, on the 2 multiplies everything, times 2 times 2 times 2. So I have 6.0 squared plus 2 times 9.81 times 2.5. Okay. So the 2 in the denominator, the halves, I took the half the other side, so that's why I multiplied by 2 here. So pressing my calculator, I have 6 squared plus 2 times 9.81 times 2.5. Then when I find the square root of the answer, it gives me 9.22 recurring 220. So I will just write two significant figures, 9.2 meters per second. So I think the answer here is going to be 9.2 meters per second. Two significant figures. Question number 3, state Hooke's law. Of course, we know that Hooke's law is only obeyed for small extensions. That's where the extension is directly proportional to uh, the applied force, because the limit of proportionality should not be exceeded. So I'll simply say for small extensions, if the extensions are very large, chances are that the proportionality limit is going to be exceeded. So for small extensions, extension is directly proportional is directly proportional to the applied force. So for small extensions, extension is directly proportional to the applied force. That is Hooke's law. Or you can just simply say extension is directly proportional to the applied force. After it is just one mark. The variation of the applied force with the extension for a sample of a material is shown in the figure. So this is the variation. Okay. The sample behaves elastically up to an extension of 80 millimeters. Up to 80 millimeters, this is elastic. That means when the deforming force is removed, the material can go back to its original length. And it breaks at point X. So at X, that is the breaking point. On the line in the figure, draw a cross to show the limit of proportionality. So limit of proportionality is where the straight line stops. So the straight line stops around here. And I said label this P. So I'll put a P here. Then on the figure, on the line in the figure, draw a cross to show the elastic limit. Label this cross with the letter E. So this is the elastic limit where the at 80, because they said to an extension of 80, the sample behaves elastically up to an extension of 80. So the elastic limit is at 80, so I'll call this one E. The sample in B has a cross-sectional area of 0.40 millimeters squared. We have to change millimeters squared to meters squared. So since 1 meter is 1000 millimeters, so millimeters squared to meters squared is going to be times 10 to the power of minus 6, because you square both sides. So it becomes power 6, but remember it is from millimeters to meters, so it's times 10 to the power of minus 6 to change it to meters squared. The initial length of 3.2 meters. For deformations within the limit of proportionality, that's where the straight line stops, determine the spring constant. So because it is within the limit of proportionality, so that means the spring constant K is going to be the gradient. The gradient of the straight line section of the graph. Straight line section of the graph. So it means the constant K is going to be equal to, so I'll just check from my graph here. This is at I think this is this 60, and then here the scale on the vertical is 0.2, so 1 2 3 4 5, that is 5.2, 5.4, so this is 5.4. Here it is in millimeters, remember, so I will say this is going to be equal to 5.4 minus 0 divided by 60. I will change 60 to meters. It will be 0. What is 60? Divided by 1000. So that is 0.06 meters. So this is going to be 0.06 minus 0. So 5.4 divide by 0.06. So this is giving me a K as 90 newtons per meter. So the answer here is going to be 90. Or I could have used the K is equal to F over X, but it's the same thing, or force of extension. Then the Young modulus of the material from which the sample is made. So we also know that Young modulus is equal to the stress divided by the strain, which is the same as, of course, Young modulus is the force over area, then divided by the stress, which is extension of original length, which is the same as the force over area times original length over extension. That is Young modulus. So I can find Young modulus from the force, which is 5.4, then times original length, which is 3.2, divide by the area. What is the area? The area is 0.4, but times 10 to the power of minus 6. So that is 0.4 times 10 to the power of minus 6 to change it to meters squared. That is the area. Then times the extension, which is 60, which was just 0.06. This is the extension. So 5.4 times 3.2 divided by 0.06 times 0.4 exponent minus 6. So this is giving me 7.2 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. So this is 7.2 times 10 to the power of 8. This is in pascals. 7.2 times 10 to the power of 8. Alternatively, from this expression, Young modulus is going to be, we know that F over E is a constant, is K, because K is force of extension. So this could be K times original length over area. So this would be K, which is 90, original length is 3.2, and then the area is 0.4 times 10 to the power of minus 6. I'm sure this would give us the same thing, because F over extension is a constant K, which is 90. So I would say K times L naught over area. That gives us the same answer. Then determine an estimate of the work done on the sample as it extended from zero extension to its breaking point. Explain your reasoning. So if it reaches breaking point, I think the only way we can find the work done here, total work done, is going to be the area under this graph. So first of all, I need to divide this into several shapes. So there are several ways of doing this, but the easiest would be to divide this into several shapes. So I'm going to divide this into approximate shapes because it's going to be just an estimate. I'm very certain the examiner may determine the tolerance. So I'm going to approximate this to a trapezium. Let me approximate this to a trapezium. Okay, so I have this part here. I don't know, that will not, but I can still divide it into a triangle and a trapezium. So let me change the colors so that I have different shapes. So I'll remove this one at the bottom. So I have the one at the bottom, that is a trapezium. Then I have a triangle on top. So I have the triangle. I'm using different colors just to show you what I'm doing. So I have a triangle. Oh, it stops here. So you shouldn't be worried. It stops here. Okay. Then I'll have this other remaining part, which I will show you its how to find its area. So I can first find the areas of these ones. The area of this one here is going to be a half times, remember, the area of a trapezium is A plus B. So A, let's say A is 200. Remember, I have to change these to meters. So 200 divided by 1000, I think that is 0.2 meters. So 200, so the A is going to be 0.2 meters plus B, let B be the shorter end, which is approximately, it is very close in the center. I don't want to use this. I have to change this. I want to use a very easy to find point. So I'm doing this all trying to find the area of a trapezium. So let me draw a horizontal line here. So I'm making this to be the trapezium. So actually this is not 0.2, it is just this point here. I think this was the hardest question in this paper. It carries very few marks. So this one is 160, which is 4. So we have 200 minus 8, that is 192, which is the same as 0.192 meters. So the area of that trapezium is going to be 0.192 plus, so between 60 and 192. So 60, 192 minus 60, that's 132. So this is 132, this is 192, this distance here. So this is going to be plus 0.132, then times the vertical height, or what I'm considering to be the vertical distance, is this distance here, which is 5.4. So this is times 5.4. So that is the area of that trapezium. So now I remain with this upper part here, which I also have to deal with. So let me see if I can move a triangle. I'm going to increase the thickness and I will change the color for elaboration. In the exam you can't do this of course. So I can remove this. So this is the area I'm going to find. And I think this is a triangle. I don't know whether I made it very clear. Okay, that is an approximate triangle, which is going to be a half. The base is 120 plus minus 192. 192 minus 120, 70. So this is 72. Then the vertical is from the vertical is from 54 to 5.4 to 1, 2, 3, 4. I think this is 6.8. So 5.4 minus 6.8, I think that is 1.4. So this is going to be a half. The base is going to be 72, which is 0.072. Then half base times height, then times 1.4. That's for the triangle. Then I have this remaining part here, which I'm going to shade with another color. This remaining part here. So I'm not supposed to do this because, of course, I will be changing everything. So I can even rub off these ones because I've finished to elaborate. I have to leave the answers which were there first. This was E. So we drew this. We have this shape here and remain with that one. So this one is a half and that. So to find this one here, the only way I will be able to do this, I can remove, if I want, I can draw a rectangle and I remain with a few boxes to count, but I will just count the boxes, full boxes. So the full boxes which are remaining, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. You can say this is approximately full 30, 31, 32. So I have 32 full boxes approximately. Then those which are not full, I'll use a different color. So every box which is crossed, you must count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20, 21, 22, 23, 24, 25, 26. I can say approximately 26. So half boxes, they're approximately 26. So how am I going to use these boxes? What is the area of one box? The area of one square, one box. On the vertical, one box is 2 divided by 10, which is 0.2. Of course, that is newtons. Times on the horizontal, one box is going to be 40 divided by 10, which is 4. But it is 4, to change it to meters, it will be 4 divided by 1,000, which is 0.004. Here it was 0.2 newtons. Here it is 0.004 meters. So newtons times meters is going to be joules. 0.004 meters. So the area of one box is going to be 0.2 times 0.004. The area of one box represents 8 times 10 to the power of minus 4 in joules. So it means the full boxes we shall multiply by that area. The half boxes we shall multiply by half of that area. So now I'm doing the working here. So it means the work done, let me go back to blue. The work done is going to be equal to the area under the graph. The work done is going to be the area under the graph. So I'm just going to give an approximate value. So note that one box is equal to 8.0 times 10 to the power of minus 4 joules. And we have got, we have 32, approximately 32 full, and we have approximately 26 half boxes up. But then we have parts which have been divided. So the first part, trapezium, is a half into So we have a half into 0.192 plus 0.1332 times 5.4. So half into 0.192, that was A, plus B, which was 0.132. Then the height, which was 5.4, plus. Then we had another triangle, which was a half times the base. The triangle which was a half times the base was 72, which is 0.072, and the height was 1.4. So plus a half times 0.072. I have to change the distances to meters. That's why you see 0.072, then times 1.4. Then we now have plus the full boxes. They were 32 times the area of one full box, which is 8 times 10 to the power of minus 4. That is the extra area which I could not convert into any shape. Then half boxes, they were approximately 26 times half of the area, which will be 4. Half of the area of one box, which is 4, times 10 to the power of minus 4. So I now just press my calculator to simplify this. So 0.5 into 0.192 plus 0.132 times 5.4. Then I'll say plus 0.5, that is a half, times 0.072, then times 1.4. Then plus, we had 32 small boxes which were full, so it is 32 times 8 exponent minus 4. Then plus, we had 26 almost half boxes, so we have 26 times 4 exponent minus 4. So this is giving us a 0.96. So the area is approximately 0.9612 joules. So that is, according to me, that is what I'm getting. Of course, I expect that when the examiner comes up with a mark scheme, he will give you a tolerance, degree of tolerance. So this could be approximately, maybe approximately plus or minus 0.2 joules. So you could get that plus 0.2, which is that, or you could get that minus 0.2. So me, I'll write here 0.96 joules. But I'm saying the examine, of course, when you do it on your question paper, because you're using a pencil and a ruler on your question paper, your answer might be very close to 1.0 joules. 1.0 joules plus or minus 0.2 joules. Your answer might be in that range. The examiner would determine the degree of tolerance, but the method is fine. Work done would be the area under the graph. I think that was the hardest question in this paper. Then a second sample of the same material. Same material means same Young modulus. Large cross-sectional area, so A has increased than the original sample. The same initial length, so L naught is the same. The two samples are each deformed within the limit of proportionality. So they are deformed with the limit of proportionality. So it means the extension is going to be actually okay. They are deformed with the limit of proportionality. State and explain qualitatively. Qualitatively means you must be very, very specific with your answer. How the spring constant of the second sample compares with the first sample. So we saw that Young modulus is equal to K L naught squared over area. We saw this because K was force over the extension. So, and Young modulus is stress over strain, which is force over area times original length over extension. So this means original length is the same, and that means the spring constant K, and of course the Young modulus is the same. So the spring constant K is directly proportional to the cross-sectional area. So we now have a larger cross-sectional area, which means we expect a greater spring constant. So I will simply say from Young modulus equals to K L naught over A. It implies that K is directly proportional to the cross-sectional area. So I will simply say the spring constant, just putting it in words, spring constant is proportional to the area. So the spring constant of the second sample will be greater. So the spring constant of the second sample will be greater. Okay, so that is the simple explanation there. Oh, I took much time on that question. Question: for a progressive transverse wave traveling from left to right is shown at any instant in time in the figure shown here. R and T are points on the wave. This is a progressive wave, so that is very easy to think about. State the phase difference between the points R and T. This is not a stationary wave, so don't think about 180 degrees because it's not a stationary wave. But if you look at R and T, this is half a cycle plus a quarter, half a cycle plus a quarter. So it means if I use T, or time out of step, the time out of step is going to be equal to a half plus a quarter of a period. Because between R and T we have a half and a quarter cycle, which is the same as 3/4 of a period. So if I want to calculate the phase difference, phi in terms of degrees will be 360 into T over the period, which will be 360 into the time out of step is 3/4 of a period, then divide by capital T, which gives us a 3/4, that is 0.75 times 360, which is 270. So if the phase difference is 270 degrees, it means anything, remember for destructive, if the phase difference is 270 degrees, it has the same effect as 90 degrees. It will have the same effect as, this is the same as 270 in pi is the same as 3 pi over 2, I think, in radians. So I would write an answer as 270 degrees, which is direct from calculation, or I would write 90 degrees. Of course, 90 cannot easily be seen from calculation. Oh, 3 pi radians, this one can also be seen from calculation. I just change 360 to 2 pi because one cycle is 360 degrees, or 2 pi radians. So the answer can be 270, it can be 90 degrees by the way, it can be 3 pi over 2 radians. On the figure, draw an arrow at point T to show the direction of movement of point T at the instant shown. So on the figure 4.1, we're going to draw an arrow at point T to show the direction of movement of point T. So the wave is traveling from left to right. So particles after R must be vibrating upwards, and after forming this trough, the particles here must be vibrating downwards. So it means that T, I'm going to put an arrow pointing downwards. So let me wrap all these. So at T, I'll put an arrow which is pointing vertically downwards. So a particle at point T must be vibrating vertically downwards. So you must use a ruler here and draw an arrow which points vertically downwards at T, because all particles on this side of the wave vibrate downwards. Because the wave is traveling to the right, after forming a trough, all particles after trough must, all particles here vibrate upwards. After forming a trough, they now vibrate downwards to form a crest. After forming a crest, they now vibrate upwards to form the next trough, and so on and so forth. So at T, the particle must be vibrating vertically downwards. So I can show you the side, just to show you the side where the particles vibrate downwards. At this point here, along this side here, along this side of the wave, along this side of the wave, along this side of the wave, the particles are vibrating downwards. Then on the other opposite side, for example, this side, they are vibrating upwards. What did I say? This is downwards, upwards, downwards, upwards, downwards, upwards. So it is the arrow must be pointing vertically downwards, because after forming a trough, the next thing is to form a crest. The only way we can form a crest is if the particles are vibrating downwards. So the answer is that arrow pointing downwards. Then the horizontal distance between R and T is 0.62. Remember, between R and T, we say that this distance or this length was representing 3/4 of a cycle. This length was representing 3/4 of a cycle. So the length of 0.62 corresponds to 3/4 of a cycle. Calculate the frequency. So I have to reduce the thickness. So to find the thickness, frequency, we know that V is equal to lambda times F. And we know that F is equal to V divided by lambda. So we need to establish the wavelength. But we know that 3/4 of a wavelength is equal to 0.62 centimeters. So from centimeters to meters, I will say times 10 to the power of negative 2 to change it to meters, which means that the wavelength is going to be 4 times 0.62 times 10 to the power of minus 2, divide this by 3. Okay. So I will now just substitute into F equals to V, which V is given as 0.27, divide by, so the 3 goes up, so it will be times 3, divide by 4 times 0.62 times 10 to the power of minus 2. So I'll check this with my calculator. 0.27 times 3 divide by 4 times 0.62 exponent minus 2. So this is giving me 32.66 hertz, or approximately I'll write 33 hertz. The wave is a water wave produced by dippers S1 attached to the vibrator in a ripple tank. An identical dipper S2 is attached to the same vibrator so that the sources are coherent. The two dippers produce interference patterns on the water in the tank as shown in the figure. The wave crests from each source are represented by solid lines, and the wave troughs are represented by dashed lines. So of course, when a crest and a trough that are perfectly identical meet at a point, destructive interference occurs. At point P in the figure, the wave from S1 has the same amplitude as the wave from S2. So that means at P, we are seeing a crest and a trough meeting, but they have the same amplitude. So positive A meets with the negative A, so that the resultant amplitude is 0. That is destructive interference. Describe and explain the amplitude of the resultant wave at P. So because it is the 3 marks, I have to write enough things that are going to give me 3 marks. For example, I'll tell the examiner that the resultant wave is formed by adding the individual displacements, or the resultant displacement is formed by adding the individual displacements of the waves from S1 and S2. So I'll say resultant wave is formed by adding the individual. That is the principle of superposition. The individual are displacements of the waves from S1 and S2. I think that would give me a mark. Number 2, since the waves have the same a path difference, which is always an odd number, because remember they are coherent and they are coherent and the waves have the same amplitude. We are noticing that a crest is meeting with a trough. Of course, when a crest meets with a trough and the waves are emitted in a phase, they will always maintain a constant phase difference. It means the waves have a path difference, which is always an odd number of half wavelength. So since the waves, of course, for destructive interference, we know that the path difference is n times lambda over 2, where n should be an odd number. Since the waves have a path difference that is always, or which is always an odd number. An odd number multiple. Let me add there multiple. An odd number, not odd, odd. An odd number, because n here is going to be 1, 3, 5, and so on and so forth for destructive interference. Since the waves have a path difference that is always an odd number multiple of half wavelength, the waves from the sources will always destructively interfere. So the waves from the two sources will always destructively the waves from the two sources will always destructively interfere. I think that is enough to give me 3 marks. I can also add, because they wanted to say, they said describe and explain the amplitude of the resultant wave at point P. The waves from the two sources will always destructively interfere. So displacement, so the resultant displacement is always 0 at P, and let me say, and the amplitude at P will be 0 at all times. So as a teacher, I encourage your students to write as much explanation as they can about a given question. As long as there's no contradiction, the examiner will always credit a correct point as long as there's no contradiction. So our resultant displacement is always 0 at P, and the amplitude at P will be 0 at all times, because there's always going to be destructive interference. Okay. Then state Kirchhoff's second law. We have already stated this law in one of the papers. So I'll just simply say the sum of EMFs around a closed loop is equal to the sum of PDs or potential drops, PDs around the same loop. We know that this is a consequence of conservation of energy because PD is energy converted from electrical to other forms, and EMF is the energy converted from chemical to electrical. So this is a law of conservation of energy. A circuit contains a cell of internal resistance small r, the two resistors of resistances R1 and R2 as shown in the figure. So the current here is I. Of course, when it reaches here, it splits into I1 and I2. Of course, let's assume that the voltmeter is high resistance voltmeter. The PD across the two resistors is V. Of course, the PD is the same. The current in the cell is I. Use Kirchhoff's laws to show that total resistance RT of the external circuit is given by R1 over RT equals to 1 over R1 plus 1 over R2. So we shall use Kirchhoff's first law first by Kirchhoff's first law. Total current I is going to be equal to I1 plus I2. And of course, the PD across each resistor is the same. PD across R1 and R2 is the same as the terminal PD, which I'm calling V. It's the same as terminal PD, which I'm calling V. And of course, we know that by Ohm's law, we know that V is equal to I times R. Since I is total current, then the terminal PDV is going to be I times R total. But for the other resistors, for I1, it is going to be, so for I1, we shall have, okay, so this implies that I is going to be equal to V over R total, and therefore I1 is going to be V over R1, and then we have that I2 is going to be V over R2. So I will substitute in the first equation, so I have V over R total is equal to V over R1 plus V over R2, which means that V over R total is equal to V into 1 over R1 plus 1 over R2. So V cancels out, which therefore implies that 1 over R total is equal to 1 over R1 plus 1 over R2. Okay, so anyway, the two marks are going to be, I think, this point here and I think around this point. The EMF of the cell is 1.5 volts. When the values of R1 and R2 are 10 and 15 respectively, the PD measured by the voltmeter is 1.38 volts. So this is going to be the terminal PD. Calculate the internal resistance R of the cell. Okay, let's first find, because we have the terminal PD, we can tell the total current which is moving through the whole circuit. Let's first find the resistance in parallel. So resistance in parallel resistance, they're in parallel, just say product 10 times 15 over the sum, which is 10 times, plus 15. So 10 times 15 divided by 25. So that is 6. Total resistance in parallel is 6.0 ohms. So I have total resistance in parallel as 6.0 ohms. That means I can now find total current in the parallel combination, which is the same as total current in the battery. So total current is going to be the terminal PD total current in the circuit is going to be the terminal PdV divided by the resistance in parallel. So this is going to be 1.38 divided by 6. So 1.38 divided by the answer. So the current is going to be 0.23 amperes. It is the same current which go through the internal resistance. It is the total current actually. Also remember that EMF is equal to the terminal PdV plus the lost volts, which means the lost volts is going to be the EMF minus the terminal PD. But the lost volts is the current through the battery times the internal resistance, which is the EMF 1.5 minus the terminal PD, which is 1.38. So it means small r is going to be 1.5 minus 1.38 divided by the current, which is 0.23. So 1.5 minus 1.38 divided by the current, which is 0.23. So this is giving me a 0.52 as the internal resistance, 0.52 ohms. Alternatively, in one of the papers, we have used the potential dividers where we say that the ratio of the resistances should be equal to the ratio of the PDs, which so this will be lost volts, or the PD across the internal resistance over the terminal PD, which is the PD outside the circuit or on the external circuit. So R over 6 would be equal to lost volts is of course 1.5 minus 1.38 divided by PD across the parallel combination is the terminal PD, which is 1.38. So R is going to be 6 times, I think this is 0.12. Then I divide this by 1.38. I think I get the same answer. 6 times 0.12 divided by 1.38, which is the same thing. So this gives us 0.52. Okay. A third resistor is added in parallel with R1. So we now have 3 resistors in parallel. The more resistors we have in parallel, the smaller the effective resistance. So total resistance is actually decreasing. State and explain the effect, if any, of this change on the current in the circuit. So remember, the current in the circuit is going to be the EMF divided by the total resistance in the circuit. But total resistance in the circuit is equal to the resistance in parallel plus the internal resistance. Resistance in parallel decreases if we add another resistor in parallel with those which were already there. So it means total resistance decreases. If total resistance decreases, total current increases. So that's number one. So we are saying total resistance decreases. The advantage of having resistors in parallel is total resistance decreases. Total resistance decreases or decreased. The tense doesn't matter. And the EMF did not change. The EMF is unchanged. The EMF is unchanged, so the current in the cell increases or will increase. Okay. Then the PD measured by the voltmeter, which is actually, I think that is the terminal PD. What happens to the terminal PD? Of course, the terminal PD is going to, I think it will decrease because the lost volts increase. Remember, I've just said terminal PDV is equal to the EMF minus the lost volts. Terminal PD is equal to the EMF minus I times R. I, so this is minus, not equals to. I has increased, which means the lost volts or the PD on the internal resistance has increased. And if the PD on the internal resistance increases, when I subtract, the terminal PD becomes smaller. So I will simply say a greater current A greater current in the cell means more lost volts. What I mean by this is greater PD across the internal resistance. Greater PD across the internal resistance. And so from what I've just described here, it means the terminal PD, which is the PD on the voltmeter, will decrease. So terminal PD, which is the PD on the voltmeter, will decrease. Okay, so that will decrease. The last question, I think, that is particle physics. I have to borrow 5 or 6 minutes. Nuclei of an isotope are samarium, each contains 62 protons, 85 neutrons. So I have to write samarium. We have total number of protons is 62, but I have to add number of A is going to be 62 plus 85 nuclear number. 62 plus 85, which is 147. So this is going to be 147. The isotope of samarium is radioactive and decays by emitting particles. Gamma radiation is not emitted, so there's no gamma emitted. The energy spectrum of the emitted particles is shown, and we see that all the particles have the same kinetic energy. So these particles are going to be, of course, they can't be beta particles. They have to be alpha particles because they have discrete kinetic energies. Explain how the figure shows that this isotope of samarium emits alpha particles and does not emit beta particles. So I have to explain both sides. So I will say, of course, the energy of the particles is discrete, or it has only one value, so it must be alpha. The energy, this was a question in Feb March, I think. The energy, I don't know whether it was in Feb March, but it is not a new question. The energy of the particles, the vertical line is showing the energy of the particles is discrete. What do you mean by discrete? That means it has only one value. It is constant, has only one value. So it must be alpha. Then on the other hand, we can also talk about beta particles. And we know that beta particles are emitted with a continuous range of energies. Beta particles are emitted with a continuous range of energies, so this cannot be a beta. We saw beta, I think, in paper 2.1, I think, or 2.2. And beta particles are emitted with a continuous range of energies, so this can't be beta. So this cannot be beta. The isotope of samarium decays to an isotope of neodymium. Give the radioactive decay equation for this decay. include the nucleon and proton number of all the particles involved. So samarium, which is SM, this was 62 and this was 147, is giving us ND plus. The isotope samarium, okay, we have agreed that these beta particles are not emitted, so it is alpha which is emitted. So I'll just add here alpha. So you can add He for 2 or just write alpha for 2. So balancing the proton number, this is going to be, I think this would be 60, and I think this would be 143. So this is neodymium and plus an alpha particle. I think I balanced correctly. Yeah, 143, 60. A baryon is composed of 3 quarks, which all have different flavors. All of them are different. The baryon has charge of 0. 2 of the quarks in the baryon are up and bottom. Remember, they are totally different. Determine in terms of the elementary charge E, the charge on the third quark in the baryon. Okay. So it has an up quark plus bottom quark plus an unknown quark, I'll call it X. But total charge is going to be 0. So an up quark has a charge of positive 2 over 3e plus a bottom quark has negative 1 over 3e plus the unknown charge should give us 0. So what is the unknown charge? The unknown charge is going to be 1 over 3e minus 2 over 3e, which gives us negative 1 over 3e. So this is, remember the quarks are totally different flavors. So it can't be a bottom. It can't again be bottom. Which particles have charge of negative 1 over 3e? We have strange, we have bottom, and we have up, down. So bottom has been taken out. So we have to choose between strange and down. So the charge of the other particle is going to be negative 1 over 3e, and state a possible flavor for the third quark in the baryon. So I said it can't be a bottom quark because they have different flavors. So this can only be a down quark, or it can be a strange. So I think this must mark the end of this paper.
My channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, as criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated.